So in this video, we're going to look at an example of adding a bunch of forces together. The book refers to it as coplanar force addition. So this is the way that these problems usually look. We have this I hook, we have various forces acting upon it. We're either explicitly given the geometry that would allow us to decompose into X and Y components, or we can just see from the drawing. Fortunately, they've chosen the coordinate system for us that would allow us to do that decomposition. And what we want to do is find the resultant force that's actually acting on that I hook. And remember that resultant force is just a fancy way to say the vector sum of the individual force vectors. So what I'm going to do is I'm going to grab a new piece of paper here, and I'm not going to try to split the screen because sometimes when I do that, this actually doesn't turn out too well. So I'm going to actually while I draw it, I will split the screen here. So let me get the actual .cam up. Good. And I can still see, so that is good. That's a requisite thing. So they've already defined our coordinate system for us, and they've told us that we're basically going to choose the point of, we're modeling the I hook as a particle or just a single point, and we're going to assume that all forces are applied at that particular point. So we know that the force F3 follows a geometry, and this is typically something that you would see in the book where they've defined the geometry by saying that if we were to decompose F3 into XY components, it would go along a triangle, which is similar to, so ignore my scale here, a 3, 4, 5 triangle. So in addition, we know that F1 acts purely in the vertical direction, and I'm going to try to be consistent of the actual magnitudes here. So if you notice for the problem information I was given, Mag 1, and the reason I said it that way is when you actually work these problems in my lab, they have this tendency of actually changing the magnitudes. They change those numbers because they're randomized. So F3 is a 580 Newton force. That's actually the largest, so I'll try to reflect that in my drawing. So there is F3. And we're told that its geometry is 45 degrees relative to the minus x-axis. And that's an important point, because one thing I want to mention is even though there is a convention for defining the actual direction of vectors, particularly from the positive x-axis with counterclockwise positive, we can always just draw, as long as we're clear what the actual reference axis is for measuring our direction. It's okay not to use that. The one thing you have to be careful when you're entering your homework, there's usually going to be some specification of what your angle should look like. So here are our three vectors. Here is our y-axis, and we're actually asked to find the resultant force vector. So remember that the resultant force vector is nothing more than the vector sum of those three forces. And I could take a geometrical approach. I could actually draw these according to scale and arrange them according to the parallelogram or the triangle rule and attempt to take that approach. However, we know that it's just going to be easier to add all the, and I'm going to say from I equals 1 to 3, the I components of all of the x components, rather, of all of those three vectors, times I hat, plus the sum of all the y components. And I will write that as a vector by scaling it by j hat. So in terms of what I am trying to do, the first thing that I need to do is to decompose each vector into rectangular components. So I'll say write each vector in rectangular form. And how will we do that? Well, I always think it's just easiest to redraw the vectors. So notice that F1, we can see it's purely aligned along the y-axis, so it naturally has no I hat component. It will only have a j hat component. We were told its magnitude was 320, so I'm just going to use that simplified notation that I spoke of earlier, and I will just call this 0, 320 newtons. So what about F2? Notice the F2, this should have been an F2, sorry about that. F2, I'm going to redraw, and this is one we want to be careful of because the geometrical information that we're given is that it is at a 45-degree angle relative to the minus x-axis. So if I write it in terms of a decomposition, one of the things I want to show you here is you can always just deal with these as scalars, like just worry about the side links of the triangle, and then use your intuition to correct the signs after the fact. So if this has a magnitude of 420, right, and I just were to view this as a triangle, and it's a right triangle, of course, and the hypotenuse is 420, and this is 45 degrees. What is, by definition, the sine of 45 degrees? Well, if I just call this Fy and Fx for now, and we're going to have to do some sign corrections, but that's okay, we would note that the sine of 45 is opposite divided by hypotenuse, right? Sine of 45
is Fy divided by 420, which means that we can define what we're calling Fy here is just taking 420 times the sine of 45. And in a similar fashion, we could find Fx by just taking 420 times the cos of 45. But what are we going to need to correct? Notice that according to what we traditionally call a positive y-axis, this guy's going in the correct direction. It's going up. However, the x component, as we've shown this decomposition here, it's going to the left. So I can manually correct and put in a negative sign here. The alternative that you might be more familiar with or more comfortable with is just to always reference your angle from the positive x-axis with counterclockwise positive. So if you do it in your calculator, you'll find that 420 cos 45 minus in front is the same as 420 times the cosine of 135. So I'm going to actually go to MATLAB and make those computations. You can use whatever calculator you want. You'll notice I've been doing a lot in MATLAB today. Hopefully, okay. Yeah, good. I didn't have any variables that I needed to store there later. So if you're familiar with MATLAB or want to download it, I know some of you are at UTSA, you have a free site license, and so do the Alamo College's students. So what I'm actually going to do to make this a little bit easier, rather than write down those numerical values, remember we talked about the importance of actually not rounding intermediate results in order to not affect our results. So I'm actually going to store the y components and the x components as actual variables, and then I will add those at the end. So I'll call the y component of f2 420 times sine d of 45, and I'll store that. I'll call the x component of f2 minus 420 times the cos d of 45. You might, if you're not familiar with MATLAB, wonder why I'm using d on the end. You don't set the mode like you do on your calculator into radians or degrees for doing this type of work. You just tell the calculator, you tell MATLAB rather, what type of unit you're entering by either including the d or not. We said f1x is going to be 0, of course. Then we said f1y is going to be 320. Let's do our last decomposition. That was for the vector f3, and this one is a little bit tricky because we're not given an angle, we're given a triangle to which it is similar. So if I look f3, let me get that going, good. We're told that it lies along or it can be decomposed into, let me actually just show you rather than talking about it. So this is the magnitude of f3, it is 580 newtons, and what we want to find is the x component and the y component. Well, we know that however this force decomposes into a force triangle, it is similar to a triangle which has a base length here of 3, a base length here of 4, and a base length here of 5. So even though we weren't given theta, we know that the cosine of theta is going to be the adjacent side length divided by the hypotenuse, which is 3/5, and the sine of theta is going to be the opposite divided by the hypotenuse, which is 4/5. So it's actually a little bit easier on us that we weren't given theta. It makes the math cleaner. So when I want to find fx, I know it's always going to be, right, the magnitude times the cosine of that angle. But even though I don't know that angle, I know the cosine of that angle. So I can substitute in 580 times 3/5. And for fy here, I can substitute in 580. It's going to be times the sine of theta. So that's going to be 580 times 4/5. And we can do that a little bit later because I'm just going to put that all in. To my calculator, I will say f3x is 580 times 3/5, and f3y is 580 times 4/5. And now that I have all of the different components, in order to add them up, I'll just say fx total is going to be f1x plus f2x plus f3x, and I will actually spit that out. That way I have my answer here. So f, the resultant vector, is going to have an x component of 51.0152. I'm not going to round because sometimes your book does this weird thing of reporting the vectors. It's not weird. It's actually somewhat common in terms of their magnitude and direction. So notice that the y component of this is really large. We'll look at why that is in a minute. But this is 1,081. And then that is all the precision that I have in newtons. So going back to my dot cam, just to show you what this vector would look like. It would have an x component of 51.0152 and a y component of, that's a 1,081 newtons. So you can kind of just sketch what this would look like, right? It's just got a little x component and it's got this huge y component. For all practical purposes, this thing is basically going perfectly along the vertical direction. And it has a y component here of 1081 and an x component of 51.0152. So does that intuitively make sense? Well, if you think about what's going on, all of these vectors are contributing to pulling this I hook up vertically. F1 purely does it vertically. F3 has a component that's vertical up. F2 has a component that's vertical up. However, in terms of the horizontal forces acting upon this I hook, the x component of F3 counterbalances or counteracts the x component of F2. F3 pulls it to the right, F2 pulls it to the left. So what that means is that the x component, it's not surprising that this isn't a very large quantity. So if I were to want to actually report what the magnitude of the force totally acting is on the hook, remember you just take the square root of the sum of the squares of the components, and that would come out to be, let me actually see what that would be. Going over to MATLAB, it's going to be, hopefully everyone knows, very similar to just the y magnitude. So if I take a square root of fx squared plus fy squared, I get something, again, that looks just like the magnitude in y, because that's basically what it is. So I'm going to call this, just rounding and using our engineering notation, the 3 sig figs. Let me actually show you on the .cam. But this is 1,082.2 newtons. So using that idea of engineering notation that we spoke of earlier, where we want all of our coefficients to be between 1 and 1,000, I would absorb 3 orders of magnitude and actually write this as 1.0822 kilonewtons. And remember that this idea of 3 sig figs actually only displaying the precision that is meaningful here. You would say this is approximately 1.08 kilonewtons. So how would I actually report the angle in this case? Well, this angle, remember, we usually report relative to the positive x-axis. How would I actually draw a decomposition? I'm going to get a new piece of paper here, since my drawing for that vector is kind of ugly. It's not kind of ugly, it is ugly. So here is my x and here is my y. And remember that this thing is basically right along the y-axis. Right there it is. This is the resultant force. So how would I actually go about computing what this angle is here? Well, if I did actually do a decomposition and show it in terms of a y component and x component, it's still a right triangle, right? And the y component has a magnitude of 1,081. The x component has a magnitude of 51.0152. So that theta is just going to be the inverse tangent of the opposite side length, which is 1081, divided by the adjacent side length, 51.0152. Remember, I'm just not rounding intermediate calculations to not lose any, to not create any inaccuracies beforehand. So I take an inverse tangent of, I have these stored, so I don't actually need to type them out. And it comes out to be 87.298, which to 3 sig figs is going to be 87.3 degrees, which is not surprising. We knew intuitively that it should be a quantity near 90 degrees. So I hope that is pretty helpful for you. Not too bad. And ignore all of this code above. It's unrelated to anything we are covering in this class. Cross your fingers for me if you're watching this tonight, because it's actually related to a research project that is due for a conference tomorrow. So I hope that you enjoyed this first introductory lecture to Chapter 2. Still pretty simple. Still, we're kind of getting everyone up to speed, forming our study groups, and hopefully trying to get everyone access to the course materials soon. That way we don't have to manually scan problems for the actual homework this week. So I will see you all again on Thursday.